this strangely shaped vehicle, performing a vertical takeoff followed by a landing. Controlled, is a prototype of the second stage of a fully reusable rocket. Called Nova. It is under development and is from a company called Stoke Space, which like SpaceX believes rockets can be operated more like airplanes, being able to return to Earth in one piece and be used multiple times. But the way they want to do it is quite different. Instead of protecting the upper stage using a massive heat shield composed of ceramic plates like the Starship or the Space Shuttle, they plan to do this using the liquid cooling system associated with the engine. Yes, partner, the second stage engine and the heat shield will work together. The Nova rocket will be composed of two different stages. They appear to be updating the rocket design, but the first stage should have approximately 3.6 meters in diameter and will have 7 engines powered by natural gas and oxygen liquids. Engines use what is called a full-flow staged combustion cycle, or full-flow stage combustion. It's the same type of cycle as the Starship's Raft engines. The working principle of any rocket engine is to already produce gases at high speed. And to do this, the engine needs to use stored energy in some way. In simple thrusters, for example, such as those that use only nitrogen to perform maneuvers. In space, this energy is stored in very high compression tanks. In launch vehicle engines, this energy is stored chemically and combustion of these propellants release this energy, generating gases and heat. But to get a rocket off the ground, you have to burn a lot of fuel. So much fuel, in fact, that it needs to be pumped into the combustion chambers. And that takes energy too. In Rocket Lab's Electron forward rotor engine, for example, this is done using a electric pump that uses power from a battery. But that is an exception. In most rocket engines, the energy for pumping the propellants is harvested, burning a small part of it in incomplete combustion. This incomplete combustion generates gases that turn a turbine connected to turbo pumps that pump the propellants. These gases can be burned in a guest generator, like Merlin from Falcon 9, who makes an incredible chemistry and throws these gases generated outside the combustion chamber. This is what is called an open cycle engine. But in closed cycle engines, these gases from incomplete combustion are not judged outside, after passing through the turbines. They are injected back into the combustion chamber. This is the case of Blue Origin's B4 engines, for example, which perform chemistry in oxygen inside what is called precamator. But engines like Raptor or the Nova first stage engines have two pre-coolers. One that does a chemical in oxygen and turns a turbo pump and another that does a chemical uncombustible and spins another turbo pump. It is a very efficient cycle with many benefits for reusability, but it is also very difficult to develop. To date, only one engine like this has been used in launches, the Motorhopter. In June of this year, Stoke Space announced that it had completed the first study of its engine, which is already a very significant milestone. These 7 engines that will equip a first stage will generate around 320 tons of thrust at the time of takeoff. The first stage has landing legs very similar to those of the Falcon 9, and it must return to Earth and perform a landing chemistry in a very similar way to rockets from SpaceX. The second stage has a very different format. It will be about 4.2 meters in diameter, have an integrated hood and a single motor driven by liquid hydrogen and oxygen. Yes, a single engine with 30 different combustion chambers arranged in a ring. This engine is of the expander blade cycle type. It is the same type of engine as the New Glenn's second stage, the B30. Unlike other engines, the idea behind this cycle is to use the heat generated by the engine itself, combustion, to ensure the proper movement of propellants. Just like any engine, it deals with high temperatures in the combustion chamber, which is a challenge. Big. They need to be cooled so they don't melt during operation. In modern engines, this is like a mind made, passing propellants through channels on the walls of the combustion chamber. These cryogenic propellants absorb this heat and keep the walls at temperatures appropriate. This can be called regenerative cooling. But in an engine like the second stage of this rocket, that is not the only function of the hydrogen that circulates through the walls of the 30 combustion chambers. Part of this fuel, now at a higher temperature, in gaseous phase, turns the turbine. That turns the turbo bombs. In engines like the famous RL-10, this hydrogen is injected into the combustion chamber as soon as well followed, but in the case of the Stoke Space engine and Blue Origin's B30, it is thrown outwards, without suffering combustion. Hence the word bleed, bloodletting. This allows the engine to be a little more powerful at the cost of some efficiency. And this turbine exhaust happens right here in the middle. And this, together with the composition of the 30 nozzles, makes the set have an effect similar to an aerospike engine. But the coolest thing about this second stage is that it allows it to be reusable. And what makes it so different from other Solgates is the integration of this engine with a shield of heat. As you can see, this stage has a capsule shape. And the bottom is a heat shield. It goes down through the atmosphere like this here, and there's no ceramic or ablative material protecting him. It's simply stainless steel. The idea is that during re-entry into the atmosphere, hydrogen is circulated through channels behind of this shield and keep it at a suitable temperature. Basically the same thing happens in the combustion chambers during operation. And best of all, the thermal energy absorbed by the hydrogen circulating there increases its temperature and turns it into gas, which turns the turbine and pumps even more hydrogen. It is a high regulation cycle. As more heat is absorbed, the more the turbine turns and the more hydrogen passes through the shield to cool it. This hydrogen is thrown out at that central point and carries heat with it, keeping all protected. And after going through much of the deceleration of the return, the engine is turned on at a certain altitude and the second stage lands propulsively. It's brilliant. And liquid hydrogen is very good at fulfilling this function because it is a substance with high thermal capacity. That is, it can absorb a lot of heat by changing very little temperature, and in addition it has a very low density, which makes everything lighter. Releases the load capacity. There are no ceramic plates that need to be replaced or may fail, or material population that is consumed to protect the vehicle, means that a system like this requires very little intervention between flights. It is ideal for reusability. The engine's 30 combustion chambers allow them to be controlled individually, ensuring orientation control during launch and landing. But since the engine is not on during the re-entry and there is no aerodynamic surface mobile as they plan to control the second stage, well, generating lift in the same way as capsules like the Crew Dragon or the Module Command of the Apollo program. As a vehicle like this passes through the atmosphere, it encounters air molecules that are deflected to different trajectories like this here. This generates a resistance force that we call drag. If the center of gravity of this vehicle has aligned with its geometric centers, these tools for the aerodynamic tools will add up to generate a resultant force aligned with its axis of symmetry. Like this here. But if the center of gravity is offset from the geometric center, these aerodynamic tools will act to align the vehicle's center of gravity with the drag force. And this new attitude will cause a change in direction for which air molecules are flexed, causing more of them to be diverted to one side, generating support. The direction of this lift can be controlled by rotating the entire vehicle, moving the center of gravity. And this is how capsules are controlled. But the stock species will do this a little differently. Instead of shifting the center of gravity, they tilted a heat shield, hitting basically the same goal. All of this generates several benefits over other approaches. The Starship, for example, needs to perform its re-entry belly up, that is, through the needs to be rigid, not only vertically, but also horizontally. Since the second stage of this rocket rises vertically and this one rises vertically, it only needs to be rigid in that direction, which is much more efficient structurally. The vehicle can be lighter this way. The problem with this is that the Starship needs to make a very abrupt change in orientation during the firing process, which is a very big challenge because the propellants run out, not staying at the bottom of the tankers. But if the vehicle is already in an upright position, this is not a problem. Another big challenge of reusing an upper stage is precisely dealing with the center of gravity. Since they are almost empty, the center of gravity is very low, that is, close to of the engines, that the most stable position for an object re-entering the atmosphere is with the center of gravity down, which is right where the engines are and where they normally. There is no heat shield to protect them. Stoke solved this by combining the two in this ingenious way. The heat shield is located near the vehicle's center of gravity during re-entry. The finished vehicle will be capable of placing up to 3 tons into low Earth orbit. In this fully reusable mode, Stoke Space knows that the second stage is the most important part of this architecture that they chose, and that's why they started working on it first. And that little polish, very similar to the first Skyspace tests with Starship, happened in September 2023. And just like SpaceX, they also decided to use stainless steel as the primary material for the entire rocket, prioritizing the manufacturing process. Of course, there's still a lot to happen, but they are definitely a company for you to keep an eye on. It's a very similar mindset to SpaceX, and this approach is unlike anything else what has been done in the sector, both in the United States and in other countries. And if you get down to it, it could actually be revolutionary. So, I hope you guys enjoyed the video. And that's about it for today's episode. Thank you so much for tuning in, and that's all for today's update. If you enjoyed watching and found it useful, please make sure to subscribe to my channel and hit the like button. And if you want to support our channel and if you want to be up to date, you can become an exclusive member, so click on our perks through the link in the description below. Thanks to watching and see you next time.